Software-defined hardware-assisted verification, scaling of the quadrillions of cycles for verification in the AI era, ensuring that the platforms can scale the industry demands and support new use cases as they emerge. The semiconductor industry at an inflection point, the convergence of advanced multi-die architecture, AI-driven workloads, and rapidly evolving the interface protocols, creating unprecedented design complexity. At the same time, the market pressures demand faster time to market and high performance, leaving the little room for error. From data center to edge development, users have to learn software and AI workloads well before the RTL is implemented into target technologies to avoid late surprises at the hardware-software interface. While the verification is under pressure, modern system defined by the workloads they run as software complexity accelerated verification must ensure the design meets stringent requirements across the functionality, power and performance, latency, security, safety, and scalability. Missing these targets can lead to costly silicon respins and delayed product launches. AI applications are characterized by software programs called workloads and large language models, LLMs, and workload complexity defined by range of software. Software applications have become more specific and thus contained to certain specialized tasks like AI training versus inferencing, or the creation of text versus image versus video, and etc. With the scope, with software complexity, concerns grow as and the users expect more applications than they before have to evolve very rapidly to stay competitive. In addition, we are facing the literal wave of AI LLMs serving the generative AI, inferencing needs from the data center to the edge, and with more doubling the size every 4 months. Figure a tidal wave of the AI training and the source of visual capitals the 8 years of consumer AI deployment in one giant timeline. This reality is driving a shift-left approach, making a critical requirement to move verification and validation earlier in the design cycle. The pooling these tasks into pre-silicon phases, teams can identify the resolved issues before tape-out, reducing risk and accelerating scheduling. The explosion of the use cases create a scale challenge. The verification is no longer about checking RTL alone. Today's workflow includes outer verification for functional correctness, software validation to ensure the compatibility with the real-world workloads, performance and power validation to meet the throughput, power and latency targets. Each domain introduced unique requirements, and the number of use cases continue to grow, and this expansion is fueled by the need for characterize and optimize end project under realistic conditions long before they reach the market. This drives a skyrocketing demand for verification cycles. Quadrillions of those cycles are not required to validate complex systems across diverse scenarios. Traditional simulation-based approaches cannot keep pace with this scale. Figure 2 illustrates the compounding complexity increased across the software, hardware, interfaces, and verification use cases. Figure 2 is compounded verification challenges. Imagine creating synopsis and AI, our memory wall is via system, and visual characteristics as well. Let's take NVIDIA as an example. After the announcement of Blackwell, NVIDIA announced the Rubin AI platform and the Rubin Ultra family to be available in 2026 and 2027, respectively. When the Rubin CPX architecture, purpose-built for massive context inference application, was announced in September 2025, NVIDIA also reported massive software-driven improvement for existing hardware product, including 2 times max Blackwell performance since its launch, and 4 times performance improvement for Hopper during its lifetime so far, and 6 times better throughput enabled by the dynamic software. For end users, this yield at the system level 2 to 4 times speed up in the RAM, up to 6 improvement in the first token latency, and 3 times the higher token output. As hardware and software grow increasingly complex and specialized, software-defined system enabled ongoing upgrade through the hardware lifestyle. Designing the silicon for this system is challenging, especially as Moore's law faces physical limits. To scale, the industry has turned to the multi-die architectures, while each die is developed in a verified like a standard-alone SoC. Integrating multiple chiplets introduces unique challenges. The hardware size continues to double to roughly every 18 months, thanks to the more than worse innovations. And the complexity of the chiplet increasingly come from the different vendors, requiring the ecosystem-level coordination of communication protocol and verification methodologies. As a result, rapid evolution of the interface IP implementing these communication protocols has become a crucial contributor to the verification complexity. To feed more data into AI algorithms to provide more intelligence inside of autonomously perform the specific task, the communication protocol evolve an astounding pace as illustrated in Figure 3, now doubling in bandwidth every 2 years. Figure 3, PCIe and Ethernet evolution. Furthermore, this data must be stored and read back at a very fast pace to reduce the lag between the request and the AI bot or agent and the actual action. Innovation in memory architecture, as illustrated in Figure 4, has been critical to push forward the ability to support the latest AI computing architectures. Figure 4 is the HBM innovations. Finally, use cases define the scope of what needs to be verified, and more the use cases are emerging at the record pace because the pressure to the characterized then optimize the end product to the workload running. The software complexity is accelerating, driving new demand for multi-die scheduling and interface IP innovation. At the same time, the silicon developed cycles speed up the state competitiveness in the fast-moving AI market. To meet the aggressive time to market goals and avoid costly spins, teams are shifting verification and validation earlier in the design process. As a result, verification scope has expanded dramatically. Designers must evaluate functionality, power, performance, and throughput, latency, security, safety, and scalability. After the first tape-out, this shift-left methodology has created a new pre-silicon verification use cases that pull most of these tasks forward the development cycle. Software-defined hardware-assisted verification (HAV). Hardware-assisted verification (HAV) has emerged as a solution, offering the capacity and speed needed to handle massive workload. But AHV itself is evolving, needs longer enough to provide a low-capacity verification platform must be specialized to support domain-specific requirements, flexible to adapt to the changing workloads and emerging protocols, future-proof to accommodate the continuous innovation. Just as the data center and vehicles have embraced software-defined architectures, verification, hardware is following the suit. The software-defined HAV introduced a new level of adaptability, enabling continuous update and enhancement without replacing the hardware. This approach ensures the software verification can scale with the industry demand and also supporting new cases as they emerge. Software-defined hardware delivered ongoing improvement through the software update, dynamic scalability to handle the growing workload, future readiness for the evolving standard and protocols. Looking ahead, the convergence of the hardware and software complexity is reshaping the verification. Success will depend on the platforms that combine massive capacity and software-driven flexibility. Just as driven updated continuously enhance the data centers vehicles, as we are now in the era and software-defined hardware-assisted verification with the requirement to deliver ongoing improvement and flexibility. At Synopsys, we are committed to empowering innovation through the continuous engineering, and we have engineered on hardware-assisted verification systems with the future in mind. Our software and hardware-defined HAV solutions enable engineers to scale verification across the industry, meeting the ever-expanding pre-silicon demand. Software demand, hardware, HAV, transfer verification. Let's make progress together, one software improved at a time. Frank Schemeier. Thank you.